Thank you, Monsieur Lemaitre, for also placing the important topic of today in the broader agenda of the EU for research and innovation, and for showcasing the pivotal role of EOSC. With this, we are going to have our last keynote speech, and for that, I'd like to invite Robbert Dijkgraaf, who is the President-elect of the International Science Council, formerly Minister in the Netherlands for Education, Culture and Science. Mr. Dijkgraaf, over to you. Do you have slides?
Thank you so much for the invitation to speak at this conference. And actually we'll have a kind of a broad overview of both the future of science and perhaps the future of Europe. And perhaps you might think what somebody once said about the young Winston Churchill, that he said, "I wish I knew so much about anything as you know about everything." So it will be kind of a broad range perspective. So where is science moving? And I would like to submit that the previous century was the century where we discovered the building blocks of reality. We discovered the particles, the genes. Let me try to see how this works. Where do I? Yeah, there you go. So we discovered the building blocks of life: DNA, RNA, proteins and genes, the particles, atoms and molecules that make up matter, and the bits and algorithms, yes, that built up information. But I think actually now, in the 21st century, it's our job to start building from those building blocks. So we are moving in the age of artificial life, of genetic editing, CRISPR-Cas, in terms of designer materials, quantum technology, and of course in the age of artificial intelligence, neural nets and machine learning. And indeed, if you think about it, for instance, you know, every form of life that you can find on the planet is just an absolutely negligible fraction of all possible genetic codes and possible organisms. And the same is true for materials and for information. So I always like these old maps of cartographers. You know, they mapped the part that was known, but the unknown, the blank spots of the map, they usually figure those kind of sea monsters. And so what are modern day sea monsters? So I'm a theoretical physicist, so I'm very happy. I know exactly what I don't know. 5% of the visible universe, so all the matter, radiation, stars and planets, makes up roughly 5% of the content of the universe. And so my sea monsters are unknown particles, dark matter, dark energy, that are comprising the remaining 95% of the universe. But I would say that actually this is a vast underestimate of what we don't know. Because it's not about what we will be discovering in nature. That's this missing part of the map. It's about everything that we can possibly build in the laboratories here on planet Earth. So the real space to discover is the space of everything that can be made out of these building blocks. And then I would say that what we know right now is like an infinitesimally small fraction of everything that's there to be discovered. And how do we navigate that infinite space that actually we will be discovering in the 21st and later century? So I think we're really at the beginning of a new renaissance of science. Because these three technologies, in life science, in material science, in information science, are really accelerating each other. Perhaps the biggest killer application of artificial intelligence is to find new materials by which you build new computing machines that then actually give even better AI. And some optimists say that the rate of progress of science will easily increase tenfold in the coming years, which means that most of us will live till the end of the 21st century, at least scientifically speaking. So where does that leave data science? So I think we probably all agree that the thing that's really kind of pushing us in this direction is this huge tsunami of data that actually is kind of washing over us. And science is somehow trying to deal with this tremendous, exponentially increasing amount of data. And how do we do this? Well, you will talk a lot about artificial intelligence, and there's been a long paradox between, some sense, the qualities of computers and human beings. They're very different. Computers are algorithmic, very deterministic. They have this kind of 2D architecture. You can easily plug in a printer or an extra screen. Our human brain is very different. It works in 3D through neural nets. It's much more probabilistic. But of course, importantly, it's adaptive and self-learning. And it's this famous paradox, Moravec's paradox, that says that the easy problems are hard and the hard problems are easy. That is to say, that what is easy for a human being, like playing football, is very difficult for a robot. We have all seen the funny movies. And actually, multiplying huge numbers is very easy for a computer, very difficult for a human being. But I think we're living in a time when this paradox is being resolved, and where somehow these two domains are flowing into each other. And often this is known as the bitter lesson. And the bitter lesson is that actually there's nothing that beats the sheer power of Moore's law and the exponential growth both of data and computing. Ultimately, that's proven the most effective way to actually get to AI and to many other applications. And I think, it's easy to see that this, a continued exponential growth, both of computing power and of data, will lead to remarkable new results. Now, if we continue, we have seen some examples already. I think most of you are certainly familiar with the spectacular result of DeepMind's AlphaFold, who solved the protein folding problem. Actually, it could only do so because decades and decades of careful work by chemists provided the very curated and precise data set that the DeepMind engineers could mine, and indeed been extremely successful. One of the deepest problems in biology: how do complex molecules attain their three-dimensional shape? And as you think all know, this led to last year's Nobel Prize in chemistry. And really interesting, by the way, this application of AI in science that also shows, by the way, the borders and the limits of these methods, because this algorithm is much less successful when it's confronted with very radically different kind of molecules. So in order to progress, it needs also new kind of data. So I think this is my grand scheme of things. So I plotted here the scale of physical effects towards their complexity. And on the left and the right, you find my domain of expertise, the smallest particles, the largest structures in the universe. We have been extremely successful to capture them with a handful of particles or a few lines of equations. But this leaves, what I like to call the messy middle, all those phenomena where you don't have a grand unified theory or a simple equation. The life sciences, the neurosciences, most of our behavioral sciences, and all the planetary science. And I think the AI revolution is promising, with the great advent of production of data, to actually address that middle part. And that raises many questions, of course. What are the class of problems where actually artificial intelligence will find structure in this great complexity? How robust are those results? Do they generalize? And can we even understand it? But it's extremely exciting to live in a time when this all will be kind of addressed. So if we move on, particular, I think, in those areas where we can create a virtuous cycle where foundational models built on good data lead to design, whether it's new molecules or new materials or new algorithms or new configurations, that then can actually be experimentally observed in laboratories, whether it's through robots or through other ways of iteration, analyze, and then you create new data This is, of course, the kind of circle which led some of the AI algorithms to be extremely successful in Go or chess, because they could play against themselves. If science can start playing against itself, we get spectacular progress. And I think this is an extremely exciting domain. And again, this all depends on providing the right kind of data. So another trend, I think, that I want to describe is the globalization of science. So if you look at this animation, you see the growth of the number of articles in science over basically the last 25 years. And you literally see other continents coming online. So this is another kind of spectacular exponential growth that we're living into. And I love this map, recent map, that shows the amount of scientific collaboration. So all the lines, this is not the diagram in the back of your in-flight magazine, but these are all the co-authors on scientific articles. And just shows, what an incredibly intimate and close-knit web we have woven in terms of scientific collaboration. And I think a third component is that if we look at modern science practices, they are increasingly interdisciplinary and transdisciplinary. So I often think of science as laying this jigsaw puzzle. I don't know about you, but I start typically at the edges where the disciplines are. And I think now we're moving again in this complicated middle part where the various disciplines meet and where also other stakeholders meet. I think an important trend is that we see more and more transdisciplinary research, which is research being done by those involved, whether it's governments, it could be neighborhoods, it could be those industry, NGOs, all those that in the end have to deliver results. And there's this famous phrase, I repeat it once more, the world has problems, the university has departments. It's not completely untrue. So often I think of bringing the wrong plug to the wrong country. So we all know this, that it doesn't really fit. And actually my service in government can add a little line to it. Government has ministries. And again, the great challenge is to work across those boundaries. I think if you think of the House of Science, it has many interior walls, it has many lowered ceilings, and I think we are in a moment where we are looking at redesigning the scientific enterprise. So let me share two quotes of Nobel laureates that I find inspiring. Here's Steven Weinberg, who said, "Most advances in science are discoveries about nature, but sometimes science makes a discovery about science." And I think that's one of the moments that we're living. That in order to produce relevant and interesting and exciting and breakthrough science, we also have, with the same critical view that we look at the world, look in the mirror and look how science is organized and operates. And the second quote is from Sidney Brenner, the biologist, Steven Weinberg, of course, famous particle physicist, architect of the Standard Model. "Progress in science depends on new techniques, new discoveries, and new ideas," probably in that order. And again, the techniques are absolutely amazing that are coming up. So it's a very, very exciting time in science and in redesigning science, and you're all part of it. But I think it's also a very exciting time in the history of Europe, as we already heard in the beautiful speech by Marc Lemaitre. So there's this big stack of reports telling us, what the future of Europe should be, what our challenges are. And my kind of one-line summary is that in Europe, the whole is often less than the sum of its parts. And actually, I would say the same we could have say about science. There are many puzzle pieces missing too. So why is this important? Well, clearly, many of the challenges of Europe, and I'd say also the world, require collaborative science and technology, whether it's energy security, climate, biodiversity, food security, clearly national security these days, and the regulation of technology. And many of those challenges, whether it's cutting-edge science, whether it's the societal challenges or the economic competitiveness, require continental scale. Also economic competitiveness. We see that the real opportunities for productivity growth are typically in those areas where scale matters. So Europe has, as its advantage, its continental scale, and has to take those opportunities. But of course, this all happens in a very worrisome background. We see geopolitical tensions, we see countries turning inwards, international collaborations often seen as a zero-sum game, which is not in science, as we have seen with the spectacular growth of global scientific collaboration. And then technology is accelerating. It's accelerating at a pace that a period of 3 months is relevant, right? You might have a new iteration of your favorite AI chatbot. And so Europe has to react to all of this. And I would say that, modern science, if you look in the history of science, you can say it's Europe's strength and it is its gift to the world. And it was born in this unique ecosystem of the 15th, 16th, and 17th century, this Republic of Letters, where there was all these different groups, kind of combination of competition and collaboration, a plurality of cultures, and an openness to the world. European science wouldn't have been there if we haven't been open in the past to outside influence. This is this beautiful graph I'd like to show, which is it's the period till the 14th century. And you see, how the various different countries and regions have contributed. So the good thing is that, there's no single country in Europe or around Europe that can claim to be kind of the dominant power. It always has been this incredibly collaborative, complex system. Now, if we look further, and I press 10 times more this button, yes, oops, I wouldn't go back. So if you look at Europe's position in science and technology, obviously it's a major player in terms of the competition with the US and China. You roughly see it in terms of the share of publications and patents. We are doing really well. This is this strong foundation that was mentioned. By the way, this graph is interesting too, that if you take the 3 big blocks, you don't cover the world. There are many other countries, what in America is always called ROW, the rest of the world, that contribute significantly. And so it's not perhaps so much about how big your piece of the pie is. It's also about what you say, can we grow a bigger pie as a world in terms of science and technology? If you look at expenditures, actually, we see that EU is not doing really well. We know we are not reaching the Lisbon goals, and there's a real challenge here, where you see particular in terms of absolute value, the US and China taking off. Of course, you all know these are largely private R&D expenditures, but yet, these graphs are good to know. And this graph, and I'm not an expert in this, but it led to a lot of worries. This was a recent review of the 64 critical technology areas, where according to this report, China would lead in 57, the US in 7, and Europe in none. So this is also something, I guess, that we should definitely worry about. So I would say, one of the things that really struck me as a very important recommendation in all those reports, particularly in the Draghi report, is that Europe should move towards a real research and innovation union. If we see our national policies, they're often fragmented, they're decoherent, and sometimes even contradictory. So it's like you have a material which is not magnetized, and these little magnets are pointing in all kinds of different directions. And I think what we need is a more alignment. And so we need kind of big magnets, not only in CERN, where we accelerate particles, or in other large facilities. But I think it's incredibly important that these research innovation policies of member states are being aligned, and that we have a common strategy on those areas where scale is needed, which might not be everything. In fact, there are many areas where you do not need a European approach. But I think certainly in this area, data management and curing data, obviously you need. And so I think it's very important that we move ahead here and indeed, have our EU instruments as powerful magnets for this further alignment. And also use smart specialization. If the sum of the parts wants to be more than, the whole wants to be more than the sum of the parts, we have to use distribution of labor, we have to avoid wasteful duplication, we have to fill critical gaps. that currently are present in the European research enterprise. And I think we also should be smart in how to do this geographically. So distributed networks where all regions benefit, not only those that are just lucky enough to host our premier research institutes or infrastructures, should be part of this collected effort. It's incredibly important that this actually is something that every region, every member state can fully support and see their strength. And I can't think of a region that does not have intrinsic strength being reflected in the collective effort. So I like this graph, whatever the metric is, it might be highly disputable, but this is this list of highly cited researchers, and I like the fact that actually the Netherlands at number 7. But of course, I also, perhaps it's kind of a little bit confrontational, that roughly the number of top scientists in my home country is roughly the same as in Harvard. So how do you look at this? Does that mean that one university can replace a whole country? I would say no. I think this shows that a relatively small country like the Netherlands can beat a major research university. However, in a more distributed way. In the Netherlands, we have 13 research universities that are all typically in the top 200, but of course none of them is in the top 10. And where Harvard educates less than 2,000 students a year, in the Netherlands we educate with these 13 research universities 100,000 students. So it's a different model. And shows again that if you take the elements and bring them together, we can build a scientific superpower. And I think that is the challenge for Europe. So I would say, Europe's strength in science, I sometimes joke, its bugs can become its features. No, I think we have a unique system based on collaboration and competition. Europe's complexity and inertia are actually advantages for a scientific infrastructure. They lead to stability and predictability. The next framework program, 7 years program, is actually, from the point of view of many national policies, an infinity. I was just saying that the average lifespan of a European minister is now less than 22 months. Openness is another strength. So starting with the 27, but then of course having 20, and I hope soon if Japan joins 21, associated countries, and many other like-minded countries that are looking for reliable associations. So Europe transcends its geography. If you look at the map of Horizon Europe, you see it's becoming a global configuration, and many other countries on that map are potential, I think, collaborators of Europe. So that openness, also in a geopolitical sense, I think is a great strength. So one way to move forward is what I like to call sector plans. If you look at the matrix of European strength, so the strategic goals that we have as a European Union, and the research networks, the question is, can we somehow optimize this matrix by thinking of that both the columns and rows are kind of maximum output. So can we build strategic alliances around key themes and then, again, use this kind of distribution of labor to make sure that in an atmosphere of trust and reliability, those research partners can concentrate on their strength, knowing that the complementary jobs will be done by other partners. And I have an image where I think of the map of Europe, the scientific map of Europe, very similar as you have maps in your atlas, where you have these beautiful geological maps, and you see certain areas lighting up in certain themes. So perhaps the map of Europe, of scientific Europe, looks very different, whether it's AI or quantum or nano or biosciences. And I think this would actually be a great strength. Finally, I think, large-scale infrastructures are a European success story. In Scrabble, it would be triple world score, because the science, obviously, world-class facilities are typically beyond the financial and organizational capacity of member states or even individual countries. In innovation, because the European way, these are open facilities where cutting-edge technology is shared in public-private partnerships, also with companies and NGOs, and create spin-offs. And of course, geopolitically, the fact that you can actually bring countries together using infrastructure. And so I'm very happy to see that in the vision of the European Commission of the future of Europe, these infrastructures, which I think are kind of the backbone of Europe science enterprise, play a dominant role. And I think, again, this is something where Europe has unique opportunities. There are many things that we can do in Europe, but there are few that probably only we can do. And I think these large-scale infrastructures are definitely part of it. But finally, if I wait long enough, yes, perhaps end with two kind of more philosophical points of view. So in this kind of three big blocks that are now coming, dominating world science, I think we see very different philosophies. I'm stealing this basically from a famous science and technology philosopher who said, like, the US is typically about markets, it's about freedom, it's about open-ended, the endless frontier, the famous phrase from Vannevar Bush. Science and technology is seen as pushing the economy and pushing away the boundaries of the unknown. China has perhaps a deeply ingrained different point of view in how they think about science and technology. It's not about markets, it's about the state. It's not about freedom, it's about security. And it's about state power, self-reliance, social control, national security, and global prominence. So what does Europe offer us? And I think the European perspective is neither on the markets nor the state, but it's much more about the citizens and their rights. So regulation, human rights, democratic values, social well-being, ethical boundaries. And I think probably all three are important elements for the future of science. But I think Europe can offer a complementary point of view that's absolutely crucial. And so in my view, the absolute key asset, the unique selling point of Europe in the future should be its soft power. There's a famous saying, politics is downstream from culture. And I think this is also true in science policy. I think our values, and these are central, I think, to your meeting here the coming days, are the academic values are absolutely critical in setting up Europe. So academic freedom, to investigate everything, especially those political sensitive subjects that are under threat around the world, whether it's climate, biodiversity, vaccines, or gender. Collaboration, fostering a collaborative, pluralistic environment where multiple perspectives are welcomed and actually seen as a strength so that we can build on each other's work. What's the next one? Openness, obviously, how could I miss that? So responsibly sharing our publications, our data, software, and other research outputs, and transparency, making the entire research life cycle visible, and I think it helps also with the quality of science. And finally, I think inclusivity and equity, ensuring that all individuals, regardless of their location or institution, can participate. And when I was recently speaking about being inclusive, somebody said to me, stop speaking about inclusiveness. Talk about expansive. It's not about how people can join your effort, but how your effort can grow and make space for other voices. And I think, again, this should be an ambitious European goal, an expanding scientific enterprise that can ensure that all individuals can contribute. And I would say not only scientists, but everybody that's involved in the scientific enterprise, which in particular also includes all stakeholders and citizens. So I think actually that would be a tremendous progress for Europeans' open science. And I'm very, very energized by the fact that you're all working on this great enterprise. So thank you very much.